Hello students, welcome back to NKT online study and e-learning platform. Let me show you something. Just one line, one tiny line of code. No AI, no operating system, no CPU. Just this. Assign y equals to A and B. Looks harmless, right? Looks like normal code. Looks like something from C. Maybe Python, maybe Java. But here is the crazy part. This line doesn't run on hardware. This line becomes hardware. Today, I'm going to show you how a text file can become a real electronic circuit. And once you understand this, you will never look at the programming the same way again. In this last video, we discovered something shocking. CPUs are not written in C, and that creates a huge question. If CPU aren't written in C, then what language built the CPU? We found the answer. HDL, Hardware Description Language. And today, we go one level deeper. We are finally going to see what HDL actually looks like. Assign y equals to A and B. Before I explain anything, I want you to make a prediction. What is this? Software or hardware? Seriously, think about it. Most students get this wrong because our brains are trained to see text and think software. But HDL plays by completely different rules. This line becomes a circuit, not metaphorically, not conceptually. Literally, when engineers synthesize the design, software tools convert it into logic gates. Those logic gates eventually become transistors, and those transistors become actual hardware. Think about that. You are not writing instruction, you are describing a machine. Huge difference. Let's zoom out. How does a text file becomes hardware? Here is the journey. Text, then RTL, then logic gates, then FPGA or SX, then real silicon. So this is the journey. First we write text, then RTL, logic gate, FPGA or ASIC, real silicon. Every CPU, every GPU, every AI accelerator starts somewhere along this path. And today you are taking the very first step. Let's compare something familiar. In C, A equals to B plus C. Verilog assign A equals to A plus B. This is the difference. What happens? The processor executes an instruction simple in C, that is A equals to B plus C. Verilog assign Y equals to A plus B. Looks almost identical, but the meaning is completely different. And this is where engineers, beginners either understand HDL or stay confused forever. C says perform addition. Verilog says builds an adder. One is an instruction, one is hardware. That single idea is the foundation of RTL design. If you understand this, the rest of Verilog becomes much easier. Now let's think bigger. A modern CPU contains billions of transistors. Do engineers create one giant file? No, that would be a nightmare. Instead, they divide the whole design into blocks. ALU, cache, controller, register file. Each block solves a specific problem and then all the blocks work together exactly like Lego. In Verilog, these hardware blocks are called module. Now, a module is a basic building block of hardware design. You can see, you can write module and name, module my underscore block, parenthesis, then semicolon, and module. A module is basic building block of hardware design. Every CPU, every GPU, every FPGA design is made from module. Modules are everywhere. Imagine building a city using Lego. You don't start with the entire city. You build a house, then another house, then a street, then a neighborhood, then a city. Hardware design works exactly the same way. A small module becomes larger module, which becomes complete system, which becomes chips. Enough theory. Let's build something and AND gate. This is one of the simplest digital design. And here is a very long description that this tiny module is real hardware, not a simulation, not a psychocode, not a real hardware. This is a real hardware, that is module underscore gate assign y equals to a and b and module. So in this, we know the inputs are A, B. Inputs are signal entering the hardware. Signal enter hardware. This is input. Buttons, sensors, data from another module. Input bring information in. Now this line, output. Output Y. Signal leaves hardware. Output carry information out. This is the answer produced by your hardware. Input comes in, output goes out. Simple, isn't it? Now the important line, the magic line. Assign y equals to a and b. This is where the hardware is described. The ampersand symbol means and. Both inputs must be 1. Only then does the output becomes 1. This single line describes an actual AND gate. And that's the magic of HDL. What's this transformation? Code circuit. We have written code and we are getting a circuit. This is the exact moment where HDL stops feeling like programming and starts feeling like engineering. You are no longer telling a processor what to do. You are designing the processor itself. Let's test it. Suppose A equals to 0, B equals to 0, then output or Y equals to 0. Now change the inputs. What happens? The output change immediately. Nobody runs a loop. Nobody executes instruction. The hardware simply reacts. And this is the first glimpse of how hardware thinks. Hardware doesn't wait. Hardware doesn't execute lines one by one. Hardware continuously reacts to signals. Always active, always ready. Keep this idea in mind because it becomes extremely important in the next lecture. Now imagine you are designing a $1 billion chip. Would you manufacture it immediately? Of course not. First you test it, you simulate it, you verify it because one mistake can be incredibly expensive. What is a waveform? This is called a waveform. You can see this is called a waveform. Waveforms show how signal changes over time. Chip designers spend hours staring at this because Waveform reveal what the hardware is actually doing. And yes, this is where debugging happens. You will soon learn how to read them. Imagine manufacturing millions of chips and then discovering a bug. That mistake can cost millions of dollars, maybe more. That's why simulation exists. Find the mistake before the silicon exists, not after. For now, remember only this. Wire means connection, reg or register means storage. That's enough for today. We will master the details later. Don't try to memorize everything at once. Here is something exciting. The same Verilog language you are learning right now is used for FPGAs, CPUs, GPUs, AI accelerator, different hardware, same language. The journey you are starting today is the same journey taken by chip designers around the world. Look at what you have done. You learn modules, inputs, outputs, logic, simulation, and most importantly, you learn that HDL describes hardware, not software. That's a huge milestone. You didn't write software, you created hardware, and that changes everything. But we are not done because there is one mystery left, a very important one. Hardware doesn't think like software, software is sequential, hardware is parallel, and if you don't understand that difference, Verilog will always feel strange. So in the next video, we will discover how hardware actually thinks. We will discover hardware doesn't think like software. And trust me, that's where things start getting really interesting. You didn't write software, you created hardware. You created module, inputs used, output used, logic described, hardware created. So see you in the video 3. Hardware doesn't think like software. Thank you for watching. If you like this video, give thumbs up, share this video with your friends and subscribe the channel. Thanks for watching. See you in the next video.